Team Chemistry, I'm back again. Lesson 1.5, Part 2. So this is probably the biggest lesson content-wise in the course, and this is going to be this particular lesson is going to be pretty heavy with content. So you might want to pause this video at different parts and take a mental break if you want. But once we get through it, we probably won't have another lesson quite as big or as heavy in the course. So we better get rolling. So we'll start with the slides. First thing we're going to look at are properties of compounds. So we now have looked at how ionic bonds are formed, how covalent bonds are formed, and so now we want to talk about the properties of these compounds, ionic compounds and molecular compounds. And once we look at the properties, we're going to try and explain why these compounds have those properties. So we're going to get into some finer details in terms of the forces within and between the compound particles. So we'll start with ionic compounds, and generally most ionic compounds all have fairly similar properties, and they're listed here. Usually they're hard and brittle, and they've got a high melting point and boiling points. So, for example, the salt that you sprinkle on your food, that doesn't melt until 800 degrees Celsius. That is crazy hot. Pizza ovens don't even get that hot. So another property is they are able to conduct electricity when they are melted into liquids, but they don't conduct electricity as solids. So we'll look at why that is coming up. And if they're able to dissolve in water, they can conduct electricity in water. So let's look at what an ionic compound really is, how it's put together. So we have looked at we've looked at this top corner. We know how the electrons are given away and accepted from the metal and the non-metal. We know how to draw the Lewis diagrams for that and show the bonding. So what we're actually doing with the Lewis diagram is showing the simplest ratio of the combination of positive and negative ions. So with sodium and chlorine, it's a 1-to-1, right? +1 and -1. But that's the simplest repeating pattern. And ionic compounds really are just this insanely huge, like almost infinite, almost endless repeating network of alternating charges. So you've got the purple and the green circles here representing the positive and negative ions that are formed. And ionic solids are just these repeating patterns of positive then negative, and it just goes on and on forever. Just insane numbers of these ions, all connected in this network structure. And so when we say the ionic compound formula is NaCl, we're just saying that that's the simplest repeating unit. So there's one NaCl right there, but you can see that it just keeps repeating over and over and over again. And however many of those units are all connected together, that's the extent of the size of the solid chunk of sodium chloride. So if you had pure water, it's a pretty poor conductor of electricity, But if you were to shake in some table salt, stir it up, and dissolve the salt, that water with the salt in it would conduct electricity much better. So any substance that can form a solution that conducts electricity is called an electrolyte. So a lot of ionic compounds are electrolytes because you can see this picture here. If you connect electrodes with a battery source and a light bulb, that water is able to conduct electricity from one electrode to the other and complete the circuit, which allows the light to light up. And if you were to just put that in pure water, you wouldn't really get the light bulb lighting up because it doesn't conduct charge the same way as having the sodium and the chlorine ions moving around in the water. So electrolytes are important in our body because they help carry electric impulses through the body. So your entire nervous system needs electrolytes because that's what sends the signals from each nerve cell to nerve cell and sends signals from your brain to your whole body and your body to your brain. We need those dissolved ions in those cells because that's what actually sends the signal from nerve to nerve. So let's try to explain some of the properties of ionic compounds. So we've looked at the model of the structure of the repeating unit for NaCl. And so we've said that ionic compounds have a pretty high melting point. And the reason is their ions are just held really strongly and tightly together by these electrostatic forces. And that's just the attraction of a positive ion to a negative ion. And that just goes on for many of those repeating units. So the attraction between the positive and the negative is quite strong, each individual ionic bond. And if you want to melt that substance, you actually have to heat it, give it quite a lot of energy before those ionic bonds start to loosen and start to move around. It takes a lot of heat energy to do that because they're just held so strongly together. Ionic compounds are hard because though that network of alternating charges resists being stretched or adjusted in some way. It's kind of like locked in. Like imagine you had a bunch of positive and negative magnets all stuck together, and then you started to build it out into this huge square shape. Imagine trying to form this into a different shape. It would be almost impossible because all the magnets are just being held together so strongly. So it's kind of the same idea. So it's very hard to change the shape of the ionic compounds. So if we had, say we had a really big chunk of salt, I'm thinking more of like the salt you would throw out on the sidewalk or the driveway to melt the snow. It comes in bigger chunks than what you put on your food. I hope you don't put that on your food because that would be a lot of salt. But those bigger chunks of salt are easy to crack or split into smaller pieces, right? We're not actually molding it and changing the shape of it, but if you bang it the right way, it will crack it right in half or into many pieces. So the reason for that is applying the force to a certain part of that compound shifts the network structure so that you don't have the alternating plus minus anymore. You take maybe some rows here and the other ones that are not hit, and the one that gets hit kind of shifts down a bit. And so what that causes is positive charges to line up with positive charges and negative to line up with negative. So this is kind of showing that in a easier to see diagram. So let's say you hit this part of the ionic compound, the solid, and forced those layers downwards. So now you can see that we've got a positive lined up with a positive, and we've got a negative that happens to be lined up with a negative. But that pairing of the positives and the negatives doesn't just happen right there. It happens all the way through the from top to bottom through that solid network. And so all of those repulsive forces now, because they've been shifted, they want to move away from each other. So that's how you're able to crack, like that's where the brittle property comes from. You can hit it and it will crack it, and that's because you're realigning the network, and then when the same charges line up, it wants to repel. But those two separate chunks are still very tightly held together within the network. So that kind of explains the brittleness of ionic compounds. So back to electrolytes. When we put the solid ionic compound into water, what happens is each water molecule, well, many water molecules will be able to surround each individual ion of sodium +1 and chlorine -1. And eventually it kind of the water works its way around each individual ion, and then it kind of pulls it off of the solid network one by one until they have all been surrounded by water molecules. And then your eyes cannot actually see the salt grains in the water because you've pulled apart each individual, get my pencil. You've pulled apart each individual tiny little ion and surrounded it by water molecules. And there's no possible way your eyes can see individual atoms or ions. They're just way too small. So that's why it looks like the salt has disappeared, but it's still in the water, but you've just broken it into all of its tiny separate little ions. So that is what we call dissolving, where we separate all the individual ions in the solution. So because those ions are able to move around in the water, that's actually moving electric charge from place to place. And so that's what an electric circuit is. It's charges moving from one place to another. And so when you have the electrodes placed in the water solution with salt dissolved in it, then you're able to connect the two electrodes because those charges are able to move through the water and complete the circuit, and that allows the light to light up. Okay, but we're going to talk about solutions and dissolving in a later unit as well. So this is just kind of a brief explanation of why that conduct electricity. So let's move ahead to properties of molecular substances. So this is a little bit less explanation going on here, but molecular elements, so remember when we talked about that previously, molecular elements being H2, O2, F2, Br2, I2, N2, and Cl2, just those 7. They're usually gases, and they're gases because they have really low boiling points. So even at really, really cold temperatures, these molecular elements are able to evaporate into gases. So they have low melting and boiling points. They also don't really dissolve very well in water. We will explain why that is coming up. As far as molecular compounds, so some examples of molecular compounds are shown down here. Carbon dioxide, water, wax, candle wax, and sugar. These are all molecular compounds, so they're made of non-metals bonded together by sharing electrons in bonds. And they have a little bit more variety in terms of their state. They can be gases, liquids, or solids at room temperature. And they have a variety of textures. So they're kind of much more wide-ranging in terms of their properties compared to ionic compounds. And we will explain why that is coming up. So the one thing that we want to understand as the big difference between ionic solids, ionic compounds, and molecular compounds is that ionic is just one big huge network, and every single ion is connected to every other one within this solid, right? So they're all linked together. They're all kind of locked in together. But molecular substances, each individual molecule is separate from every other molecule. They are individual particles, you can think of them. So we've got these water molecules here, and one molecule is itself a separate unit. It's not all locked in together because they don't have ion charges which attract them very strongly to each other. So that's a huge difference between ionic compounds and covalent compounds. So the big thing that can explain a lot of the properties of molecular substances is the strength. Oh, get my pencil back. The strength of the interactions between the individual molecules. So we've got some dots here showing that, yes, water molecules do interact with other water molecules. And every single molecular compound interacts with all of its different molecules. So there's some amount of attraction no matter what the molecular compound is, but some of them have much stronger attractions and interactions than others. So we're gonna explain what those interactions or attractions are and how they work, and we're going to also rank the strength of them, and that's going to help us understand and explain a lot of the properties of molecular compounds. So here's a table kind of comparing different properties for ionic versus molecular. And so we didn't really talk much about the molecular compounds in terms of their conductivity, but basically they're opposite of ionic compounds. So ionic compounds are pretty much always solids, whereas molecular could be any of the three states, and it has to do with how strongly the individual molecules attract and stick to each other. So molecular things also tend to be more soft or waxy or flexible, but they could also be crystalline, where ionic compounds are pretty much always hard and brittle. And they have the opposite property in terms of melting and boiling points, opposite properties in terms of conductivity when dissolved in water, and conductivity in the liquid state. And so we've already mentioned a bunch of examples for each. So that's just a comparison. All right. So we're going to start to get into some finer details now, specifically looking at molecular compounds and looking at the bonds within the molecules. So this term polar might be new to you. So we're going to talk about what polar means, and we're going to look at both polar bonds as well as the entire molecule and whether the entire molecule is polar or not. And that's going to lead us into understanding how individual molecules interact with each other, whether it's strong interaction or really weak interactions. So in order to talk about polarity, we have to remind ourselves about electronegativity. And that was one of the trends that we talked about in lesson 1.3. So if you remember back, the trend of electronegativity, it's the ability of an atom, when it's in a bond, to attract the electrons that are in that bond toward itself. So if you're more electronegative than the other element that you're in a bond with, you're going to be able to pull or hold the electrons in that bond closer to yourself. And then the other atom will have less of a pull on those electrons. So that difference in the pull of those shared electrons is going to affect the character of that bond. So we're able to look at the electronegativity values for, say, two different elements that are in a bond. We can read those off the periodic table. So let's look at an example here. Like we said already, elements that have high electronegativity values are really good at pulling the pair of electrons toward itself. And we know the trend of electronegativity goes up. So higher electronegativity at the top of the table and towards the right side of the table. And the most electronegative element on the periodic table is fluorine. It has a value of 4.0. So that's the maximum value for electronegativity out of all the elements. So it's actually the electronegativity difference when you compare one atom to the other in a bond that decides whether you have an ionic bond or if it's covalent bonding, if it's sharing. So it's kind of like it's a scale. So it's not like you have ionic bonding and you have covalent bonding and there's nothing in the middle. It's a range, it's a scale, so it's relative. That's what I'm trying to say. It's relative. So you could be very ionic, you can be pretty ionic, you can be a little bit ionic, you can be mostly covalent, or you can be purely covalent. It's a range, and it has to do with the difference in electronegativities of the two elements in the bond. If that makes no sense at all, we're going to look at an example. So water is a good example to start with. So look at the electronegativity values for O and H. So O is 3.4. I'm going to write it in here. Hopefully this shows up. It doesn't really show up, does it? How about pink? 3.4. That doesn't show up either. I'm going to write it to the side. 3.4 for oxygen. And hydrogen is, I think, 2.1, 2.2. Okay. So that's the electronegativity value for the two elements. So we can look at either bond, it doesn't really matter. So let's just look at this bond here. Oh, that's my highlighter. Is it? No. Okay. Let's look at this bond right here. We know that there's two electrons in there, right? And they're being shared between O and H. So the difference in electronegativity, we can write that as a short form. The triangle represents delta, so that just means the change or the difference in electronegativity. So delta En equals 3.4 subtract 2.2. So the difference in the electronegativity values is 1.2 between oxygen and hydrogen. And let's keep that in mind as we go to the next slide. To predict if a bond is ionic or covalent, we have to calculate the difference in the element's electronegativities. So we just did that. This is called the electronegativity difference, and it has this symbol here, delta En. So this value for the difference will tell you how likely it is that an electron is shared or transferred from one element to another. The bigger the difference in electronegativities, the more likely that the bond is ionic, or the more ionic the bond is. So let's go back. We saw that the difference in values for water between O and H is 1.2, which is pretty high. It's not crazy difference, but it is notably different. And we didn't really talk about this yet, these two colors. So part of the water molecule is more positive and part of the water is more negative. So we can kind of understand why that is, because O is more electronegative. So it's actually pulling the electrons in that bond toward itself. And it's also pulling the two electrons in that bond toward itself, right? And so if it's pulling electrons from both directions toward itself, then that means the electrons are spending less time over here, which means that side of the molecule is slightly more positive. And since they're being pulled toward that side of the water is slightly more negative most of the time. So this is leading us up to the idea of polarity. So we're going to look at another example of a bond. So we've looked at sodium and chlorine many times. We know sodium gives away an electron to chlorine, and we can look at the electronegativity difference for that bond. Chlorine is 3.2 for electronegativity, and sodium is 0.9. So the delta En is 2.3. That's a lot bigger difference than H and O in water, right? So this is actually quite a large difference, and it indicates that in the tug of war for the electrons, chlorine basically totally wins that competition, and it's able to not just shift them over toward itself, but it's able to completely take the electron away from sodium, and that's what makes the sodium a plus ion and the chlorine a minus ion. It's this 2.3 value indicating a very strong difference in the pull on electrons. So how do we actually know what values cause a bond to be covalent or to be ionic? Well, like I said earlier, it's relative. It's a kind of a scale, and we just, in chemistry, we kind of set up these artificial boundaries or artificial values to place them into categories. So if you have a difference in electronegativity in a bond that's bigger than about 1.7 or 1.8, which we can see here, if that difference is above that cutoff, we typically call it an ionic bond. And so the difference here for sodium and chlorine was 2.3. So it's well within the ionic bonding zone. And so that would mean electrons are totally transferred from a metal to the nonmetal, and we have an ionic bond. Let's go back and look at the water. Remember we had a difference of 1.2? Well, that fits within the middle zone, which is covalent bonding, so sharing, but it's polar covalent, which means that they're sharing the electrons, but they're not sharing them equally. Polar meaning one side versus the other. So in that case, the oxygen is pulling the electrons more toward itself, even though it's still sharing with the hydrogen. And so polar covalent bonds would range anywhere between about 0.4 or 0.5 difference up to 1.7. And then you've got the case where you have a very, very small difference in electronegativities. And in this case, chlorine bonded to chlorine, well, it's the same element, so there is no difference. The delta En for a chlorine-chlorine bond is exactly 0, right? So this is what we call nonpolar covalent bonding. So we're sharing the electrons, and it's not polar because they are shared perfectly equally. And we know that because of this value here. There's no electrons being pulled to one side or the other. They're just shared totally equally because those two atoms have the same electronegativity value. And so that's just another picture there of showing the scale from non-polar covalent all the way through to very strongly ionic. And you can see here like these electrostatic color-coded pictures. I really like these. They show you what parts of the molecule or the compound is more positive and more negative. So the more blue, the more positive you are, and the orange or red shows more negative. So you can see this F2 is perfectly symmetrical. There is no side that's more blue and one side that's more red. The colors are perfectly spread out and symmetrical there. So it's a non-polar covalent bond. HCl is quite polar, so it would be in the middle zone, polar covalent bond. You can see that there is some difference here. There's one side of the molecule that's a little positive and the other side is a little negative. And then when you go to the extreme, the shift in electrons is so strong that fluorine actually pulls the electrons completely onto itself, which makes it an ion. It has full ownership of that extra electron, and sodium has totally lost it. And so you can kind of see that there's a division there between the two different ions. There's no sharing going on. And we have a big difference here between the dark blue and the strong red on each side. So hopefully that makes sense, using electronegativities to figure out whether a bond is nonpolar, polar covalent, or ionic. So that is specifically bond polarity. looking at the electrons within one individual bond. So if we have a noticeable difference in electronegativity, then we do have polar covalent bonds. And so that means the electron density is focused more around the more electronegative atom. So the end of the molecule therefore has a slightly negatively charged end, or pole. That's where the word polar comes from. So slightly negative is represented by this symbol here. Delta negative. And so if you see that, that's indicating that one side is slightly negative. It's not a full -1 charge, it's just a little bit negative. So it's not an actual ion. And the other end of the molecule is the opposite. There's less electron density, so it's slightly positive. So the slightly is the delta sign with a plus. And so here's a picture of that H and Cl. If we look up the electronegativity difference, well, H is 2.2. And what was chlorine again? 3.2. So the delta En here is exactly 1. And that fits kind of right in the middle of the polar covalent zone. So the electrons are shared, but they are pulled slightly more toward chlorine. And this is just a simple molecule with one bond in it, right? So this is showing here that if you were to divide this molecule in half there, that the side where chlorine is located would be slightly negative because it pulls those two electrons more toward itself, and H would be the slightly positive side because it's not as good at drawing the electrons toward itself. So it's unequal sharing, and so it makes it slightly negative on one side and slightly positive on the other. And so that is what we call a polar bond. So the polarity of these covalent bonds depends on how big the difference is in electronegativity. So with HCl, we had a difference of 1. And you know, the closer you get to a difference of 1.7, then the more polar you are for your covalent bond. So let's look at 3 different examples here. So we've got HH, an HH bond. Of course, the difference in electronegativity is 0 because they're the exact same element. So that would just be 2.2 minus 2.2, which is 0 difference. Nitrogen and hydrogen have a difference of 0.9, so it is polar. The nitrogen is here and the hydrogen's here. Nitrogen is kind of pulling the shared electrons more toward its side, which makes it slightly negative, and the hydrogen slightly positive. And OH we looked at already. We saw that it had a difference of, well, this image is telling us 1.4. I think it was 1.2 that we calculated above. Yeah. So you might see slightly different electronegativity values depending on your source. But anyway, this is saying 1.4 for the OH bond, and this is the most polar out of these 3 examples. So oxygen will be slightly negative. It will be more slightly negative than the nitrogen will be. And the hydrogen here will be more slightly positive than the H bonded to nitrogen. So it's all relative. It's all on a scale of more polar or less polar. And so this is leading us up to being able to understand and explain the properties of different covalent compounds. it has a lot to do with this concept of polarity. So we've looked at the polarity within bonds, and now we want to zoom out a little bit and look at polarity of an entire molecule. So the concept is the same. If we can see whether each of the bonds in a molecule are polar or not, that is going to determine whether the whole molecule is polar or not. So it works the same way. A molecule would be considered polar if one side of the entire molecule is slightly negative, where the other side of the molecule is slightly positive. Did I say positive? Positive and negative. Anyway, it's late. I don't even know what I'm saying anymore, but I hope it's right. So if there is no slightly positive and slightly negative sides to a molecule, and it's all evenly distributed in terms of the electron density, we would call that a non-polar molecule. And it's the same concept as a non-polar bond. Okay. So let's look at some examples of polar molecules. Well, HCl, that's really easy because the molecule itself is made up of only one bond. So all we have to do is analyze that one bond, and then we're analyzing the entire molecule at the same time, right? So this is a polar bond. We already know that. And so therefore, since the molecule itself of HCl is made up of just that one bond, it would also be a polar molecule. It has to be. Now, water, we're not really going to talk much about this in grade 11, but water, the shape of water is like an upside down V. And water also has two lone pairs of electrons. If you drew out the Lewis structure, Lewis diagram for the water molecule, you would get H's bonded to O with two lone pairs. So the way water arranges itself is that the lone pairs kind of stick up from oxygen and the bonds move downwards. But that plays a role in whether water is polar or not. So if we analyze the separate bonds, this one here and this one here, we already know that those two bonds are polar, right? The electrons are being pulled up to oxygen from that bond as well as being pulled up from that bond. So if we cut this molecule in half, then we could say, let me get my blue or my red here. Red indicates more negative, and blue indicates more positive. So the side of the water molecule where oxygen is would be more negative, slightly negative, and the hydrogen side on the bottom would be slightly positive because of the two bonds that are pulling electrons in the same direction, upward, so that they add together and make the molecule of water polar as well. So water has polar bonds which contribute to making the water molecule polar as well. So that's a case where there's two bonds and they add together to make one side of the molecule more negative. So we do have to consider the 3D shape of molecules when we analyze them to see if they're polar or not. You may have tried this at home. If you rub some sort of like wool sweater or something fuzzy on a plastic hairbrush and charge up that hairbrush. If you get a skinny stream of water coming out of your tap and you bring the, not an Apple Pencil, but if you bring the brush close to the water stream, you'll notice that it starts to curve and be attracted toward the brush or the piece of plastic. And that's because each water molecule has a slightly positive and slightly negative side to it. So if you charged up a strip of plastic and added a whole lot of extra electrons on it, then this would be a very negative object. And so it's going to attract the positive side of water molecule. So since water has negative and positive sides, it can be attracted to negative things or positive things. It's just going to flip itself, and then that side will be attracted. If this was a positively charged yellow object, the water molecules would turn the other way, and the slightly negative side would be attracted to it. So that's kind of explaining why this can happen. So give it a try and freak out your families with your magical powers and chemistry knowledge. Non-polar molecules. Well, it's pretty self-explanatory what non-polar molecules are. There is no side of the molecule that's slightly negative and slightly positive. It's evenly distributed electron density, and our 7 diatomic molecules that we've looked at many times now are definitely non-polar because they're just made up of the same 2 elements and there's no electronegativity difference. So they are definitely non-polar, and that's important to remember. But there are other molecules that are non-polar as well, and it has to do with being symmetrical. So take a look at CO2 here. CO2 is made up of a double bond to oxygen on the left and the right. So really these 2 connections to oxygen are exactly the same, but they're going in opposite directions. So oxygen is more electronegative than carbon, so it's going to pull the electrons out toward it on that side for those 2 bonds, and this oxygen will pull the electrons closer toward itself on the left. But they're going to pull in opposite directions in equal strength, right? So we don't have a shift of electrons to one side of the molecule and not on the other side. It's an even pull on both directions. So that means that CO2 is also non-polar. We don't have a slightly negative end and a slightly positive end. And so in a sense, those 2 pulls from the oxygens cancel each other out, and they don't add together. Where our example of water here, they added together, right? Because oxygen pulled upwards from the 2 H's, and so those pulls added together in the upward direction. So now that we understand polar bonds and polar molecules, we are going to move into our final concept, maybe the most challenging concept to wrap your heads around. Makes sense for some people. Other people have some difficulty understanding intermolecular forces. But basically, this concept of intermolecular forces is what explains how attracted separate molecules are to each other. Some, like I said back at the beginning, some are not very attracted to each other at all, and other molecules have a really strong attraction to each other. And so we'll look at intermolecular forces and understand what they are and how they explain properties of covalent compounds. So the first thing we want to do is understand the difference between intermolecular, and intramolecular. They sound similar, but they are very different. So intra means within, inside, or between. So intramolecular forces means inside the molecule. So that is talking about the actual bonds that you're making inside the molecule or inside the compound. So that would be your covalent bonds or your ionic bonds or metallic bonds that we're not talking about this year. So it's the actual bonds within the molecule, right? So if I talk about water, intramolecular forces would actually be these two bonds. They are forces that hold the hydrogen and the oxygen together, and it's within the molecule, if you consider this thing the molecule. So that's not what we're talking about now. We're talking about inter, which means between separate molecules. So here is a picture of that. So it's not the actual bond between hydrogen and chlorine. That is your, that's your intermolecular force, the bond. But in between separate molecules of HCl, you have intermolecular force. And compared to the intramolecular force, intermolecular forces are a lot weaker than the actual bonds inside the molecule. But this is what we're going to be looking at, this attractive force or interaction between separate molecules. And there's 3 different kinds of them that we need to understand, and they range in strength from really weak to quite strong. So before we get into that, take a look at the data in this chart. I'll give you a few seconds as I have some water, but you might notice one of these things is not like the other, just like on Sesame Street. Does any one of these, perhaps the one that I bolded, stand out as not really fitting into the pattern here? Water doesn't seem to match all the others. It does match in terms of the mass. So the mass of water is 18, and it's similar in mass to all these other compounds, but it's very different in terms of melting point and boiling point. Those are both much, much higher than all of the other ones. So why is that? We're going to explain why that is. Why is the boiling point of water and its melting point so much higher than the boiling and melting points of other small molecules that are close in size to water? Well, it's due to the very high strength of the intermolecular forces in water. So, a little bit of physics here for you. Every intermolecular force can be explained in terms of electrostatic attraction. And you may not realize it, but you already know the rules of electrostatic attraction. Like charges repel, so positives repel positives, negatives repel negatives, but opposite charges attract, right? Because we know all about that in ionic bonding. So that's the concept here for any intermolecular force. If you have opposite charges, then they're going to attract each other. So the three types of intermolecular forces are London forces, or also known as dispersion forces, dipole-dipole force, and hydrogen bonding. And so dispersion or London forces are very weak. Dipole-dipole are stronger. And hydrogen bonding is the strongest. So we're going to go through each of these three and kind of explain what they are. So nonpolar molecules, it might seem that they have no way of attracting each other because they have no side of the molecule that's slightly positive and slightly negative. So how are they going to attract each other? Well, it is possible to turn those gases into liquid if we cool them down enough. So that does indicate that if they don't stay gases even in cold temperatures, they are able to attract each other enough so that they change state to a liquid. So there must be something that's attracting the individual molecules like those together. But what is that force? Well, that's the weakest of the three forces. Back in 1930, Fritz London suggested that the motion of electrons inside an atom or a non-polar molecule could result in very, very short lasting dipole moments. What on earth is that? I'll show you. So let's say we've got a helium atom. Helium has 2 electrons. So this is going to be a really easy example here. So at this point in time, we've got this helium, the nucleus, and the ring of electrons. So at this instant in time, let's say we took a picture, and those 2 electrons that are flying around the nucleus just happen to be both of them on the left side of the atom. So if we cut it in half, they're both on the left side right now, and there's no electrons on the right side. So this is an instantaneous, uneven distribution. It's not even because the electrons are both on the left side. So at that exact instant, it means that, again, if I split this in half, the left side is more negative and the right side is more positive because the left side has 2 electrons and the right side has none. So that's at that exact instant, right? Electrons fly around so fast, but that at that exact instant, we have a little bit of a dipole, a polar atom. And because of that, when this right side is slightly positive, it can actually cause an atom close to it to shift its electrons over to the left side because positive attracts negative. So that's called inducing a dipole on the neighboring atom. So because at that instant the right side is a little positive, it can actually draw the electrons in this helium atom to move over to the left side, causing the left side to be slightly negative and thus the right side slightly positive. And so these are super, super weak forces and also very quick. They're over in like less than a millionth of a second. But that is the concept of a London dispersion force. It's the instantaneous attraction of electrons in one atom to basically the nucleus of the other atom. Because in this atom, they're feeling the positive pull of the positive nucleus because the electrons happen to be over on the left side at that instant. So it opens up the positive nucleus to attract the electrons on the other atom over to the left side. This is one of the most difficult ideas to wrap your head around in the course, but the main thing that you want to get out of this is that London dispersion forces are super weak and they are super quick. They last like less than a millionth of a second for each one. But here's just another explanation of the same thing, this time just with more electrons in the atoms. So think of this one atom as having an electron pileup. They're all circling around the nucleus, but at any given moment, there might be a bigger collection of electrons on the left side, which would make this side of the atom slightly negative. And so the nucleus, which we know is positive, is not really being shielded on the right side. So that positive nucleus is able to apply an attractive force to the electrons in the atom next door. And so that causes them to shift over to the left. And now we have this interaction of the slightly positive side of that atom to the now slightly negative side of the other atom, and that is an electrostatic attraction. It's like a slightly positive and a slightly negative magnet having that instantaneous attraction that lasts, like I said, so fast, like it's done before you can snap your fingers. But that's what a dispersion force is. And that's just another diagram showing the same thing. Instantaneously, one side is more negative, and then it causes an attractive force to the other, which is more positive. So the idea here is the more dispersion forces you have within a molecule, the more they add up to a stronger overall attractive force. And what makes more dispersion forces? Well, it's all about electrons. So the more electrons you have in your molecule, the more dispersion forces are possible. So if you look at the carbon family of compounds that bond to hydrogen, so CH4, SiH4, germanium H4, and tin H4, those are all in the same group as carbon. But what do we notice about this trend here? The boiling point is getting higher. That means that the molecules in each of these compounds are having a higher attraction to each other because it's causing them to boil. It's causing a higher temperature for them to boil. So that means that they are more attracted to each other, and it takes more energy for them to separate and turn into a vapor. So what's causing that stronger attraction and the higher boiling point? Well, how many electrons are in CH4? Carbon has how many? 6. Or is it 12? My goodness. Brain is not working tonight, is it? ptable.com. Yeah, 6 electrons, and then there's 1 each in the hydrogens. So in total, we have 10 electrons in each molecule of CH4. How about SiH4? Well, now we're up to 14 plus 4. We've got 18 electrons. More total electrons, so more dispersion forces possible, therefore more attraction of an SiH4 to another SiH4. GeH4, we're now up to 36 electrons total in that molecule, and tin with hydrogen, 54 electrons. So you can see that the trend is the more the electrons, the more dispersion forces attract the separate molecules together, and that means that it takes a higher temperature to boil those compounds and separate the individual molecules. And so there's just a summary. As the size of the non-polar molecule goes up, you have more electrons in them, and so that increases the strength of the temporary dipole. So as nonpolar molecules get larger, their boiling point, or BP, increases. And we see that in this example chart right there. Okay, we're getting there. 2 more intermolecular forces to look at. This one is dipole-dipole forces. And these are a lot stronger than dispersion forces. They exist between polar molecules. So we looked at some slides previously how to determine if a molecule is polar. So if you do have a polar molecule, then one side of the molecule is more negative than the other, and this is not a temporary thing. This is a permanent thing, because the bond, the difference in electronegativity, is pulling the electrons permanently to one side of the molecule. And so these dipole-dipole forces, because of that permanent polarity, it's a much stronger attractive force between separate molecules. So HCl, chlorine is the more negative side and hydrogen is the more positive side. So opposite charges attract. And so you have this attractive force, which is called a dipole-dipole force, because one molecule is polar and the other is polar, and so dipole-dipole, 2 different molecules interacting. Here's another example, HBr. Bromine is more electronegative than hydrogen, so you have a slightly negative attracted to a slightly positive. Dipole-dipole force within HBr as well. But not all dipole-dipole forces are equal. It depends on the difference in electronegativity. So the delta En in HCl bond was something like 1.2, if I remember right. But in HBr, the delta En is, let me see if I can find it here. Bromine has electronegativity of 3, and hydrogen's 2.2, so 0.8. It's less of a difference. So this dipole-dipole force in HBr is not quite as strong as in HCl because of that lower difference in electronegativity. But it still qualifies as a dipole-dipole force because it is a permanent polar molecule. Some more data here comparing HCl versus F2. So F2 we know is non-polar because a bond between 2 Fs has a delta En of 0. So we can only have London forces, which are very weak. HCl is very polar, and so it can have dipole intermolecular force. It also has London force. Everything has London forces because everything has electrons, but dipole is a lot stronger force holding the HCl molecules together. And look at this. The boiling point of these two things is different by 100 degrees. And that's because of the dipole-dipole force in HCl. It's such a difference in attraction that it takes 100 extra degrees to boil HCl versus F2. So you can see that we're able to apply the concept of intermolecular forces now to explain the physical properties of these compounds. So there's some summary points of what we just talked about. If you're polar, you have a much stronger attraction than something else that's a similar size but is nonpolar, which we just saw here. They have basically the exact same mass and a huge difference in boiling points. So that means if you have polar molecules, they have much higher boiling points and melting points compared to nonpolar molecules. Okay, we're just about there. Hydrogen bonding, the strongest of the three intermolecular forces. So take a look at this chart. And the trend here, we can see this line is continuing upwards or downwards if you go the other way. But then the other ones all do something different when they get to group 2. They shoot up. Isn't that weird? They shoot up. So there's something going on here with the boiling points. The trend is broken with NH3, HF, and H2O. Something is causing those boiling points to be a lot higher than the trend would indicate. So what is up with the strangely high boiling points of those three molecules? And why does the pattern not happen with CH4? Why doesn't CH4 jump up in the same way? Well, it's all about hydrogen bonding. There must be some super strong intermolecular forces going on between those three molecules. So, what is hydrogen bonding? Well, it's the strongest intermolecular force. In a sense, it is a dipole-dipole interaction as well, but it's a very special kind. These are very polar molecules. HF, HO, and HN bonds are very polar. So let's look at a 3D diagram of these. So this is NH3, this is H2O, and this is HF. NH3 has one lone pair on the nitrogen. So there's 2 electrons here in this little red cloud. And we already looked at water. We know there's 2 lone pairs of electrons on the oxygen. And fluorine, because if you do the Lewis structure, F has 3 separate lone pairs on it. So that's why we've got the 3 different red clouds where those lone pairs exist. Those lone pairs come into play and help create an even stronger interaction, which is called hydrogen bonding. They're involved in the attraction. They make the more negative side of the molecule even more negative than other molecules. So it just creates a super negative end to the molecule. And so to have hydrogen bonding, this is the condition. You need to have hydrogen attached to one of the most electronegative elements. And there's only 3 of them. Hydrogen has to be bonded to nitrogen, oxygen, or fluorine. Only those 3. Otherwise, hydrogen bonding is not possible. So because of them being very polar, those bonds, it makes hydrogen become very positive on that side. So we can see a bunch of different pictures here, but let's start with HF. So HF is a polar molecule, but it's a special type of dipole-dipole interaction because it's between hydrogen and fluorine. And this is a very polar molecule. And since hydrogen is bonded to F, that means it qualifies as being a hydrogen bond. So hydrogen bonds are dipole-dipole interactions, but they are just a step above because they just have that extra big difference between the slightly negative and slightly positive side of the molecule. It just makes for an even tighter attraction. Here's a hydrogen bond between NH3, so the slightly negative end for nitrogen and the positive end for hydrogen. So you can have hydrogen bonding between 2 different molecules here, water and NH3. This is ammonia, common name. So there's another hydrogen bond. This hydrogen is attached to an oxygen and this nitrogen is attached to a hydrogen. So that qualifies as a hydrogen bond as well. Hydrogen bonding exists between molecules of water. So that's going back to explaining why water has such a high boiling point. Water can actually make a bunch of hydrogen bonds at the same time to different water molecules. You can see them all going on here. You can actually create up to 4 hydrogen bonds to 1 water molecule at any given time. And so that creates such a strong glue holding water molecules together that it has a boiling point of 100 degrees. So that's why these 3 molecules have such a high boiling point compared to the others. They don't follow that trend downwards. CH4 doesn't follow that trend because it doesn't create hydrogen bonds. CH4 looks like this. So hydrogen in this case is not bonded to fluorine or nitrogen or oxygen. So it's not a superpolar bond, and this is not a polar molecule at all either because it's symmetrical and all the bonds cancel out. So we don't even have a polar molecule at all in CH4, and that shows why the boiling point is so low for CH4, whereas the other 3 shoot upward because of that hydrogen bonding. So there's just a quick picture of hydrogen bonding. You can have 4 different water molecules, all hydrogen bonded to water at the same time. Remember that there's 2 lone pairs on the oxygen, so we're able to have this interaction between hydrogen here and oxygen because of that lone pair, and the hydrogen and the oxygen because of that lone pair, which results in a total of 4 outside water molecules able to interact by hydrogen bonds to that one in the middle. So the hydrogen bond attraction is so strong between molecules, it explains the much higher boiling points compared to other non-polar molecules that have only London dispersion forces, which we know are much, much, much weaker. So we did it. We got through all 50 slides. This is a big one, and I'm proud of you for getting to the end. We probably won't have another monster lesson like this for the rest of the course. An hour and 20 minutes. Holy cow. I gotta end this and put the video up, and then I'm going to bed. So I'll see you on the next one.